So at some point during an integral calculus class, one learns about functions that have no simple or closed form antiderivative. And these are sometimes called non-elementary functions. Well, today I'd like to look at one such function and actually find its antiderivative, but we'll have to bend the idea of what we consider a simple or a well-known function in order to do this. So our goal is to find the antiderivative of the cube root of 1 plus x cubed. And to get started, I'd like to compare this with the antiderivative of the square root of 1 plus x squared, which you would evaluate using trigonometric substitution. We would set x equal to the tangent of theta. That means that 1 plus x squared is the secant squared. So when you take the square root, you get the secant. And then dx is also the secant squared d theta, given the tangent secant derivative rules. And so this transforms into the antiderivative of secant cubed theta d theta. And then, well, I'll let you take it from there if you want to find a closed form for that. But that's not our real goal here. So maybe before we get started, I'd like to point out that the technique that we're going to use here is found in this really nice book on maybe generalized trigonometry that I'll put a link to in the description. Okay, so here's what we're going to be motivated by. So let's consider the unit circle. So let's get a picture of the unit circle or something close to the unit circle here. And recall that the unit circle is parametrized by cosine theta, sine theta, or by the cosine function and the sine function. So I'm going to parameterize this with the variable t. So cosine t, sine t. And just to really fill in all the details, this is parameterizing the following curve. And that curve is x squared plus y squared equals 1. And here we take x equal to the cosine of t. We take y equal to the sine of t. And this all works because sine squared t plus cosine squared t equals 1, the so-called Pythagorean identity for the trig functions. So what I'd like to do here to get started is to look at a different curve. And this curve will be the curve absolute value of x quantity cubed plus absolute value of y quantity cubed equals 1. So I need to put absolute values there because, well, the negative parts won't turn positive when we cube them, whereas they do when we square them. So, well, what's the graph of this? Well, it's going to be, well, a circle, but a little bit fatter than a normal circle. So sometimes these are called fat circles. So I'm going to draw a picture of this. I'm maybe like overemphasize the fatness here, because since this is cubed, it'll be like a little bit closer to a regular circle. Okay, and then, well, what's this going to be parameterized by? Well, the thing is that this curve is not parameterized by any well-known elementary function, but it will be parameterized by some function. We'll just define the functions to be the functions that parameterize this curve. And maybe motivated by our cosine and our sine up here, I'm going to call this cosine underscore 3, so the cosine 3t, and sine underscore 3. So in other words, what we have here is we've got, well, this curve defined by the equation absolute value x cubed, absolute value y cubed added together up to 1, or with this picture over here, is parameterized by, well, our formula x equals this cos 3t, and then y equals this sine underscore 3t. Okay, well, observe that since these parameterize this curve up here, well, what do we know? Well, we know that if we take their absolute value and cube them and then add them, we get the number 1. Or maybe let's look at the case when both are bigger than or equal to 0, just to get the absolute value out of there. What we have is this third cosine cubed plus this 3 sine cubed, or this sine 3 cubed, added together equals 1. Okay, well, now how could we come to grips with exactly how to define these functions? Because maybe perhaps defining them so that they parameterize this curve, doesn't uniquely define them. But I think, we could get a unique definition if we build towards maybe solutions to an initial value problem. Initial value problems have unique solutions. So let's go over here and let's recall that, well, when both things are positive, they satisfy this equation x cubed plus y cubed equals 1, where I'm taking x to be this cos 3 and y to be this sine 3. And then let's differentiate this formula. So differentiating this formula, we get 3x squared times x prime plus 3y squared times y prime equals 0. But then we can pretty easily move some things around here to get x cubed times x prime equals negative y cubed times y prime. Now, well, let's just take some nice values of x cubed and y cubed so that, well, this equation is satisfied, and we'll say that our functions cos 3 and sine 3 are defined by, well, what we take for these definitions of the derivatives. And that'll be x prime is equal to negative y cubed, and then we'll have y prime is equal to x cubed. So if this were true, well, then this equation over here is most definitely satisfied. Okay, but then also let's observe that we need some initial values, and maybe motivated by the cosine of 0 and the sine of 0, let's say that x evaluated at 0 is 1, and we'll say that y evaluated at 0 is 0. Now, let's put a box over here, and what we'll say is that our cos 3t and our sine 3t, these are the unique solutions to this system of differential equations. Okay, and I guess maybe I should say this is x equals the cos 3 and y equals the sine 3. Okay, well, let's observe that immediately we've got some derivative rules just based off, this defining property. We have the derivative with respect to t of this cos 3t is equal to minus this sine 3t all cubed. And then we have the derivative with respect to t of this sine 3t is equal to this cos 3t quantity cubed. Okay, so, well, now that we've looked at this a little bit, let's see how we can use this setup, these functions defined by this initial value problem, this system of differential equations, or parameterizing this fat circle, can be used, in fact, to solve or to evaluate this integral. Okay, so we just waved our hands at the definition of these nice functions that parameterize a fat circle. And, well, they could also be seen as the unique solutions to the following system of differential equations. And then, well, now that we've got this cos 3 and this sine 3 function, we can define the tan 3 function, the secant 3 function, and so on and so forth. And those will also be defined similarly, and we can build derivative rules as well. So we can define the tan 3 of t as the sine 3 of t over the cosine 3 of t. But then we can use the quotient rule to find the derivative of tangent, and in fact it's secant squared, just like it is in the case for regular sine and cosine. So I think that's like a nice thing that happens. You don't get any more complicated of a derivative like you do up here for the original functions. Furthermore, we can divide our original like Pythagorean type identity, or three Pythagorean identity, if you will, by the cosine cubed, and we'll get this formula down here. 1 plus the tangent 3 cubed equals the secant 3 cubed. Okay, so now we're armed with all the tools that we need in order to work towards evaluating this integral of the cube root of 1 plus x cubed. So motivated by what we learn in an integral calculus class, let's take the substitution x equals tan 3t. Okay, well, like we had before, that means that dx will be equal to this secant 3t quantity squared dt. And that means that this cube root of 1 plus x cubed is going to be this secant 3t, by this stuff over here. Okay, so let's see what this does for our integral. Well, I think it's pretty clear that what we're going to get is the integral of the secant 3t all cubed dt. Okay, and then, well, how can we evaluate this? Well, we can in fact evaluate this using a pretty similar strategy to what we would do if this were the regular secant. And that's, motivated by this fact that the derivative of tangent 3t is secant 3t. So let's split this up as follows. We'll write this as the antiderivative of sec 3t, and then sec 3t squared dt. And then what we'll do here is a round of integration by parts. So let's set u equal to this sec 3t. But what does that make du? Well, maybe I'll let you calculate it out if you want to, but observe that this is 1 over cosine. Actually, let's calculate it out. So this is 1 over cos 3t. So let's see, we're going to use the chain rule here. So this is going to be -1 over cos 3t quantity squared times, well, the derivative of cos 3t, which is minus sine 3t squared. Well, let's notice that these minus signs cancel and we're left with sine squared over cosine squared. In other words, we're left with tangent 3t squared dt. So that's one thing that differs here between our normal derivative rules and our derivative rules in this new setup. Usually the derivative of secant is secant times tangent. But in this new world, this 3 world, if you will, the derivative of secant is tangent squared. So that's pretty cool. And then, well, let's see. Let's finish off our integration by parts setup. We'll set dv equal to this sec 3t squared dt. But that means that v is equal to, well, this third tangent function. Okay, so let's put a nice green box around that. And then, well, let's do a round of integration by parts and see what we get. So let's see. So integration by parts formula is u times v. So let's see, u times v. That'll be the secant times the tangent. So here we've got secant 3t times the tangent 3t, and then minus the integral of v du. But then we've got a tangent and a tangent squared. Those will multiply together to give us a tangent cubed. So here we have minus antiderivative of tan 3t cubed dt. Okay, but then what would we want to do with this? Well, let's use our Pythagorean trig identity. Well, not really Pythagorean, maybe 3 Pythagorean, because we're in this fat circle world, and rewrite this tangent cubed as the secant cubed t minus 1. Okay, so, well, let's see what we get. So this is going to be the secant 3t times this tangent 3t, and then minus, Well, let's see. We'll have the sec 3t cubed dt, and then minus the integral of dt. Well, minus negative the integral of dt because we've got two minus signs there. So that's going to be plus. I'm just going to write it as t because we can integrate that out. Oh, but now let's look at what we have here. We have over here this setup. We have the integral of the secant cubed is written in terms of the integral of secant cubed. So, well, we could add one of the brown underlines to the other side and get two of these integrals. So we can divide by 2 and we'll have our, well, at least not our final answer, but a nice solution with no more integrals. So in other words, in the end, we'll have 1/2 and then t plus this sec 3t and then this tan 3t. And then of course, plus a constant, if you will. But now we can do our substitution back in for our original variables. So let's see, we've got 1/2. And then, well, observe up here, if x is equal to the tan 3t, then t is equal to, well, the inverse tan 3, or the arctan 3. So I can write this as arctan sub 3 of x. Well, and then of course, we know secant is this 1 plus x cubed, the cube root of that. We know the tangent is x. So here we simply get plus x times the cube root of 1 plus x cubed. And then out here we have plus a constant. Okay, so there we have it. We have this antiderivative, but since this is like something that's most definitely not very familiar, let's go ahead and do a check by taking the derivative of this right-hand side to make sure we get this object over here. Okay, so we got our antiderivative, but now we're going to check that this actually works out. But in order to do that, we need to know the derivative of this arctan 3 function. Okay, so, well, how can we do that? Well, we'll do this using our standard strategy for finding the antiderivative of an inverse function. So let's say y is equal to this arctan 3x. But observe, that's the same thing as having x equal to this tan 3y. But now we can take the derivative of both sides using maybe implicit differentiation, and we'll have 1 equals y prime times this secant 3y all squared. But then we can take this secant 3y and rewrite it, well, using this formula over here, taking the cube root of both sides. So this is in fact going to be equal to y prime times, well, what is it going to be? It's going to be 1 plus the tangent 3 of y, and then that's going to be all cubed, and then it's going to be to the 2/3 power. That's what's going to make everything work out here. But then, of course, this tan 3y here is simply equal to x. So then, well, we could write this as y prime and then 1 plus x cubed all to the 2/3, or solving for y prime and then rewriting y prime as the derivative of this arctan function. We have d by dx of this arctan 3x is equal to, well, it's going to be 1 over 1 plus x cubed all raised to the 2/3. Okay, so that's like kind of gnarly looking, but that'll in fact work here. Okay, so let's now actually do our check. So let's take the derivative with respect to x of this 1/2 times arctan 3x plus x times this cube root of 1 plus x cubed. I'll leave off the plus c because obviously if you take the derivative of a constant, you get 0. So let's see, I'm going to have a 1/2 out front of everything. This derivative of the inverse tangent function will be 1 over 1 plus x cubed all to the 2/3. Now we've got to use the product rule for this next term. Derivative of x is 1. So that's going to leave us with 1 plus x cubed to the 1/3. So I'm going to write it like that, just so when we combine terms, it's a little bit simpler. And then, well, now it's going to be x times the derivative of the rest. So what's that going to give us? So notice we're going to get a 3x squared that comes out. We're going to get a 1/3 that comes out. So the 1/3 and the 3 will cancel. But then the x squared will combine with the x to give us a x cubed. And then, well, we're going to have a 1 plus x cubed to the 1/3 minus 1 for the chain rule part. But that's going to give us a 2/3 in the denominator. So that'll be, like I said, 1 plus x cubed to the 2/3. Okay, so something that looks a little bit like that. But now let's give ourselves a common denominator, which is clearly this 1 plus x cubed to the 2/3. So if we multiply this middle term by, that over itself, we'll have 1 plus x cubed to the 2/3 down here, and then that'll build this exponent all the way up to 1. But now, well, let's add all of those things. We'll have 1/2, then we have 1 plus 1, which is 2, plus x cubed plus x cubed is 2x cubed. And then here we have 1 plus x cubed to the 2/3. But now let's observe that this 2, or this 1/2 here, will cancel this 2 down to a 1, this 2 down to a 1 as well. And we have 1 plus x cubed to the 1 power over 1 plus x cubed to the 2/3 power. But then putting that all together, we'll have 1 plus x cubed to the 1/3 power. In other words, we'll have the cube root of 1 plus x cubed. So, well, that checks everything out. We checked that we in fact have the right antiderivative by taking the derivative. And that's a good place to stop.